Good morning or good afternoon, ladies and gentlemen, depending on where in the world you are. We get a truly international audience again today, and I'm pleased to welcome you to the second webinar in the series, Scientists Empowering Scientists. Today we will talk about achieving the impossible, large patch pipettes, large tips, long tapers, and beveled or polished tips. My name is Jan Dolzer. I'm the product manager for patch clamp systems here at Sutter Instrument. The agenda for today, I will show you a few very brief housekeeping slides, mostly about getting audio and a couple other housekeeping items. Then Adair Oesterle will talk about making unique shaped pipettes. Pooneh Bagher will talk about experimental application for micropipettes. She will show us how a number of those pipettes that Adair introduces can be used in real life in real science. Telly Galiatsatos will host the question and answer session, and in the end we will have a very brief survey. Very brief, 5 quick questions, mostly along the lines of, was it only you who watched the webinar? Were there multiple people? That helps us gathering what the attendance, the interest level was it useful for you? Did the time work out? We realize today's a holiday in a few European countries. Sorry about that. Whether you want to be in your mailing list or whether you want us to get in touch with you about anything. How can you get audio? Well, if you don't hear me now, you don't hear what I'm saying here. Audio should be transmitted over your internet connection. So if you have computer speakers, turn them on. If your computer does not have speakers, or if you don't hear us, dial in at the number closest to you in your webinar control center, control panel on the right. The international numbers are listed there, and I'm listing them again here. The access code for today is 225-061-384. I'll leave that up for another 10 seconds for people who have not gotten audio yet. Looks like attendees are still dialing in. If you have any questions, use the Q&A section in the session control panel. We have 2 speakers, so unless it's very clear, please let us know which speaker the question is directed to, whether it's Adair or Pooneh. And all questions will either be addressed in the Q&A session at the end of this webinar, or we will get back to you by email within the next couple of days. We have documentation materials. You can download PDFs of the presentation slides, again through the Webinar Control Center, which by default is on the right of your screen. You can download the PDFs there. We're also recording this webinar, and the recording will be available on our YouTube channel within probably the next 2 weeks. We will repeat this webinar next Thursday at 8 p.m. Pacific time. That's a time that's more geared to our customers in Asia and down under. And we will combine the Q&A session of both webinar recordings essentially, and then post that on our YouTube channel. The previous webinar that is on our YouTube channel already is very popular. We have over 1,400 views in 9 months, considering that there are no naked ladies or cute puppies in the webinar. That's quite impressive. And everybody who has registered for this webinar will receive an email notification when the recording becomes available. Let me announce our upcoming webinar, Time for a Paradigm Change. This is about the IPA patch clamp amplifier system. And here is a URL that you can reserve at, or if you go back to the email invitation that you received for this webinar, there's also a link that allows you to register for our upcoming webinar. That will be Tuesday, the week after next. And then we will also repeat that at a later time in the day for, again, our Asian and Oceanian audience. With that, let me introduce the first speaker of today. Adair graduated at Scripps College and then went through UC Santa Barbara, San Francisco State, San Francisco VA Medical Center, ended up at Sutter Instrument, has been there for almost ever, and is today the applications engineer and the product manager for the filament-based pipette pullers. And the title of her talk today is Making Unique Shaped Pipettes. We do see your monitor. Yep, you're good to go.
Okay, thank you. First, I'm going to go over just an outline of the talk, and we're going to discuss pipette morphology, the filament and glass alignment in the puller, and a traditional approach to pulling the patch pipettes, how to make your patch tip larger, how to make very, very long patch pipettes, which is often a challenge, how to make long injection, aspiration, and cannulation pipettes, how to score and break the glass, how to do a one-sided manual pull, which gives you a very long taper, and how to bevel the tip, how to fire polish the tip, and also how to bend the taper shoulder or shaft of your pipette. Here's the puller that most people are working with these days, the P1000. We also have the P97 puller, which is the previous model. And the main thing here that we need to focus on is does size matter? And with all these various applications we're going to be going over, it's a very important issue of making sure that your pipette is the right size. So yes, the answer is the answer. And whether you're doing microinjection of zebrafish embryos or mouse embryos, or whether you're doing some other type of application, you really need to focus on the shape of the pipette. Is it long and slender? Is it short and stubby? Is it long and slender and small at the end, or is it large at the end? So depending on what your application is, determining the morphology. Here is a patch pipette where you have a tip that's probably about 5 microns, and most of the time you don't want a tip this large when you're doing patch recording, but in some situations it requires a larger tip. I'll show you how to do that today. How to make a very long patch pipette, how to make an aspiration or cannulation pipette with a clean break. You might want to bevel the tip because you might be taking that pipette that you made with a long taper. You might be putting that into the brain or into the spinal cord, and you want to make sure that you're not creating a lot of damage in the nerves and in the brain and spinal cord as you advance that pipette. And in some situations, you might want to have the tip polished because you're going up and sucking onto a membrane, or you're washing cells, or you are holding on to something and you don't want to damage the membrane of the cell or the egg. And then here is a bent tip. I can show you how to do this today too on the puller. So one other thing to review here is the alignment of the filament over the air jet and also around the glass. This is described in the Pipette Cookbook, pages 9 through 18. And there's also a video online that shows you how to install a filament and how to get everything aligned properly. Here, this is a review, and basically you want to make sure your filament is centered right to left over the air jet. And if you see here, there's the air jet is right here. There you go. And then over here on the right is the filament installed perfectly centered over the air jet. And when you know it's perfectly installed over the air jet, visually you can see that this raised brass, there's an equal amount of raised brass on both sides of that filament. The other thing you need to do is put in this program right here and pull a long taper, and then you want to make sure that both tapers are the same length. So this is in pages 17 and 18 in the Pipette Cookbook. And if your filament is too far to the left, you're going to be pulling a pipette where the left needle is longer. And if the filament's too far to the right over that air jet, the right pipette's longer. So what you want to do is you want to make sure that that filament is perfectly centered over the air jet. Both of your tapers are going to be the same length, and then you're going to have a nice smiley face. So make sure that this is the condition of your puller before you're trying to pull pipettes. The other thing to make sure is that the filament is perfectly centered around your glass. And here's your box filament. And here's where the glass should be sitting, right in the middle. And to do that, you would use the eccentric adjustments described on page 10 in the Pipette Cookbook. And there are adjustments that allow the filament to be moved up and down, right here, and also adjustments to move the filament block assembly front to back. So that's very important for making sure that the glass is getting a good balanced heat, and then also this will allow your program to be stable. The puller also has this function of looping, where if you put a one-line program in and there's zero pull and a low velocity, the program will cycle and loop back and read that one line over and over again until the glass has separated. So in 2 loops, you're going to pull the glass a little bit longer, and as you loop more and more times and heat and cycle through that glass more and more times, it becomes shorter and the tip becomes larger. So the more loops, the shorter the taper, the larger the tip, and the lower the velocity is allowing more loops, and a higher velocity is allowing fewer loops. So when you're making a patch pipette, you traditionally want to find the midpoint velocity of the velocity range that allows you to loop 5 times, for example, and that middle velocity is going to allow for a stable program. If you use a velocity setting over here on the edge, as the jaws become hotter, you're more likely to loop 4 times, and as the jaws are cooler, you're more likely to loop 6 times. So that's why you want to use a value right in the middle of the velocity range. So traditionally, when you're pulling a patch pipette for whole cell patch or dissociated or cultured cells, you're going to use thick-walled glass, and you're going to loop 4 to 5 times, and that's traditionally what your pipette's going to look like. And when you're doing slice patch recording, you're going to pull a longer, slender tip, and you're using thin-walled glass to maintain a more open lumen. But what if you need to make the tip larger? As we've discussed, if you want to make the tip larger, you might want to loop more times than what's traditional. So with thick-walled glass, you might loop 4 to 5 times. With thin-walled glass, you might loop 2 to 3 times. That's average. That's the most common. If I wanted to make the tip a little bit larger, I think, well, maybe I should just loop 1 or 2 more times. So with thick-walled glass and thin-walled glass, if I try that, I'm going to go from a pretty pipette to a pretty ugly pipette where the glass breaks off real rough. And this is not what I want for a larger patch pipette. And what's happening here is the cohesive factors of the glass are not allowing the glass to separate at tip sizes over 3 microns. So what you really need to do is write out your program into multiple lines. Here I'm having one line read. It's a one-line program that normally loops 5 times. I've written it out to 5 lines here. I've got this line repeat mode on the P1000, makes it easy. And then on the last line of heating, the last cycle, I am reducing the heat on the last line to allow for the tip to be a little bit larger. So if I adjust the heat or maybe the velocity and I reduce both of those values, the tip's going to be a little bit larger, and I'm going to be able to get closer to that maybe 3, 4, or 5 microns I want. But it's still difficult. So here's also the example with using thin-walled glass. I've got a 2-line program. I've reduced the velocity on the second line. I've made the tip a little bit shorter and a little bit larger. But if I really want to go beyond this, I want to get beyond that 3 micron threshold, what I'm going to have to do is I'm going to have to use larger glass. I'm going to have to go to 1.65 OD glass or 2 millimeter OD glass, where the glass is somewhat thin-walled. And here in this situation, I use a similar program, a similar patch program, but with this glass, because the lumen started out larger, the ID, I'm able to achieve maybe a 3 or 4 or 5 micron tip. So I'm looping 3, 4, or 5 times traditionally with this glass. So so I can go from a smaller tip to a little bit of a larger tip, where here I have a velocity of 55, I'm looping 3 times, a velocity of 45, I'm looping 4 times, and a velocity of 35, I might be looping 5 times. And the more times I loop, the larger the tip's going to be. And this glass seems to withstand this larger glass. So I can go beyond these thresholds of getting a 1, 2, or 3 micron tip using this larger glass. So that's the trick there. Now, say I want a really long patch pipette. The longer I pull the taper, traditionally, the smaller the tip is. So what I usually have in the puller is a 2.5 box filament. And how am I going to get a really long taper with this? Well, basically what I'm going to do is I'm going to disregard all the great advice that I normally give people, and I'm going to put in the following program. I'm going to put in a program where I've used thick-walled glass, and I'm putting in a value of the velocity that's much higher than traditional. And I'm letting the glass kind of run away on the first cycle of heating, and then I have enough glass left to then cycle through a few more times, 2-3 more times, and then I can maintain this 2 or 3 micron tip at the end of a very long taper. So again, I've got the thick-walled glass. My ramp value in this situation is 525. And here's the result. Look at this. It's a very long taper, and I've maintained a very good traditional patch pipette where the tip is about 1.5–2 microns right here. So here's the actual pulling of the pipette, which I'll show you. And I'm going to play the video. So here I've got the 2.5 box filament. It's heating up. Again, remember my velocity is 45 instead of something lower, and it's letting the glass really run away on the first line of heating. There we go. Look at that. And then I'm cycling through real short, quick cycles, and then I can make sure that tip remains fairly large at the end. And here it is. Look how long that is. Isn't that nice? So what if I want to get the taper even longer? Well, what I want to do in that situation is I want to install a very wide box filament, a 4.5 wide box filament. And this will heat a wider section of glass. And I have the same approach using a velocity that's higher on the first line, and then on subsequent lines, the velocity is lower. And in this situation, my ramp value is 825. So make sure you run that ramp test before you put the heat in, because you don't want to burn out your filament. But here I have a wide filament. It takes more current to heat up that filament, so that's why the heat is much higher. Again, I'm using thick-walled glass, and here it is. I'm going to be pulling the pipette. It's a very wide filament, as you can see. And it's going to melt a wider section of glass. Again, see that velocity was 50, so it ran away. And then I still have enough glass to cycle through it. And there, I'm using the 2.5 wide box filament. So here's the result, a very long taper that's maybe about 10 millimeters long. And I still have a good 2 micron tip at the end. Another type of pipette I'm going to go over here is making a very long, slender pipette where it's kind of like a straw almost. And the tip is large. It's 25 microns, 50 microns, 75 microns, or even larger. And there's various applications here mentioned that these pipettes are used for: membrane tension, membrane elasticity studies, cell adhesion studies, and cannulation, which Pooneh Bagher will be going over a little bit later after my talk. So first we want to pull a very, very long taper. And what we want to do is we want to put in, with our 2.5 box filament, or even a 3 millimeter box filament, we want to put in a heat that's slightly over the ramp value. Now, the larger your filament, the higher that heat setting can be. And then I'm going to put in a really high velocity. I'm going to have 0 pull and 0 cooling. The pull, I don't want to pull it hard, because basically if I engage the pull and I pull in the glass real hard, it actually reduces the glass pretty rapidly. It might pull a long taper, but it's going to be pretty wispy and thin. So I want 0 pull, and I want the heat to be high and the velocity to be high. So, and again, the filament width is going to determine how wide a section of glass you're melting and how long you can get that taper. So here is an example of pulling a very long tapered pipette. I have no hard pull. It's going to just drift apart real gradually. There we go. Here, there are examples in the cookbook, Chapter 10. It shows you how to score and break the glass back. You can use a glass-on-glass technique, or you can use a ceramic tile. The ceramic tile is used when you want to break the glass over 100 microns. You can also use it for 50 or 25 microns, but I like using the glass-on-glass technique because you can feel the glass a little bit better with the glass that you're using to score it with. Here's an example of scoring the glass using the glass-on-glass technique. If I were to score it here, it would be about 25 microns. About halfway down, it's 50. About maybe 1/3 the way up, it's at 75. And here, about 1/4 the way up, it's around 100. So I'm going to score it at 75. Here's an example. I'm using the larger, thicker part of the other pipette, just rubbing it gently, a little bit like one note on the violin string, and then pushing it over, and it breaks off clean. Sometimes it's not so easy, and I'm going to show you this, because you might all run into this if you're trying to score the glass maybe at a tip smaller than 20, 25 microns. The glass at this point is too flexible, and anything that's smaller than 25 microns is unable to be scored and broken most often. There we go. So you will definitely run into this if you're trying to score the glass under 25 microns. I can do it occasionally at 15 microns, but it's difficult. And here I am rescoring the glass. So I've scored it at 50 microns, and I realize, you know, I really need it at 75. So I'm just going to score it a little bit lower using the larger, thicker part of the other pipette. And I'm going to show that to you in slow motion because it's so much fun. Look at that. Isn't that fun? I mean, this is just an amazing art. Now I'm going to show you how to score the glass using the ceramic tile. I'm using the ceramic tile where the logo's on the front and the front edge of that tile is rough. I've just gently touched it, and it breaks with a clean break. So you get this flat, clean break, and you are so excited, you say, oh my God, this is so exciting. So you might want a pipette that is actually a taper that's even longer, and you might want to score the glass back at 150 or 200 microns. In this situation, and you have like a narrow filament, in this situation, you're going to want to do a one-sided manual pull. Now, you want to hold the left puller bar in place. The right puller bar is going to be moved to the right after the glass softens in about a 1.5 second duration of travel, and you're going to do that gradually with your other hand, with your other finger. And once this puller bar goes all the way off to the right and the glass separates, you are letting go of the left puller bar immediately so the glass does not melt into the filament of the glass that's remaining inside the filament. So let me show this to you. The glass heats. It takes about 5 seconds, 6 seconds for it to soften. You'll see the puller bar move to the right a little bit. And that right puller bar, I'm going to just push sideways gradually. And I get this really long taper. It's like a cat whisker. And that pipette I can score at various locations. Up here, it's going to be 50 microns. Here, it's going to be around 100. Here, it's about 150 microns. And here, it's around 200 microns. Normally, your glass pipette at this location, when you pull it two-sided, is going to be around maybe 50 microns. So now I've used a stick wall glass. I've pulled it on a one-sided pull, used all the molten glass to pull this really long taper. And now I can get a much larger pipette. So I'm going to score at 200 microns. I'm using that tile and just gently just rubbing it just a little bit, and I just go above the location where I scored it, and I push it over, and it breaks off clean. So sometimes you want to take this clean break, and you want to go and advance it into the brain or spinal cord to inject maybe stem cells or a drug. So what you need to do is to have that pipette go through in the cleanest fashion through all that nerve tissue is you want to bevel it. If you don't bevel that pipette, you're going to get some damage to the nerve tissue. You might get if it's a survival study, you might get an opiate response in the animal you don't want. So here's the beveled pipette. This is the end result. And here's the beveler, and I will show you how the pipette is beveled. Basically, you put it in the clamps, you tighten it in, you adjust the pipette to the position where it's towards the back of the beveling plate. You adjust the angle and you drop it down with the coarse and the fine adjustments on your manipulator. And then you don't want to push too hard on the plate. You just want a nice pressure. So then you get this really nice bevel. What you need to also make sure that you're doing is you are not beveling the pipette with too short a time, because what happens is this tip can be kind of squared off if you don't bevel long enough. And the other thing happens is if you're putting too much pressure on the plate, the pipette is kind of bending upward, and then you end up getting kind of the bevels down here, and then this ends up being kind of squared off. So make sure that you are beveling for a complete duration where that tip is nice and clean at the end. You got a nice clean bevel. So here again is your beveled pipette. And here on the right-hand side, you can see the beveling surface. You can see these diamond granules all over the place. That's what's causing the pipette to bevel. Here's an example of using the fire polishing spacer. Now what I'm going to do here in this situation is I don't want a beveled pipette. I want the tip to be smooth. And I want it to be smooth because I don't want to damage the cells or the eggs that I am sucking onto or pulling into the pipette. So I'm going to use this fire polishing spacer. And here's this threaded screw that is adjustable. So when I put this in place, I push the puller bar forward and I put it in place. The tip is positioned exactly either in the filament or at the edge of the filament, depending on what I want to do. I want to put it at the edge of the filament if I'm making a patch pipette and I'm just making the tip a little bit larger, a little smoother. If I'm making a cannulation needle, I'm going to put that pipette further into the box filament when I'm heating it. So here is your fire polishing mode on your puller. I have a heat and I have a time, but I have no pull and I have no velocity. So this controls the level of heat and also the duration of heat when I'm polishing the tip. If you do not have a microforge, this is a really nice trick to use on the puller. Microforges, a lot of labs have them, but if the filament's broken on your microforge or it's not working or you don't have one, you can use the puller to polish your tip. Here again is a fire polishing spacer, and here is the tip that has become smooth after you've polished it. Here's a video on polishing the patch pipette. I place the fire polishing spacer in the cutout on the puller bar. I've adjusted the screw so the tip is right at the edge of the filament. And then I just polish the tip a little bit. I have a heat setting of ramp -100 because I'm just polishing the tip. I'm not heating up the entire shaft of glass as I would be doing when I'm making the pipette. Here is an example of polishing the glass where I'm polishing the tip after I've pulled it and scored it. So in this situation, I slide the glass forward, but I hold the puller bar forward with the fire polishing spacer. And in this situation, I can get a light polish to a very heavy polish. On the left-hand side here at the top, I've done a light polish where the heat is ramp -50. Here, I've used a ramp test value to polish the tip. And here, I've used ramp +50 to make an even more extreme polish on the tip. And again, I'm using the heat of ramp or ramp +50 or anywhere in between. And then I've got a certain duration. You can control that duration also. And in this situation, in the middle, I've almost closed off the tip, and I might want to use this as a device to hold down tissue or hold down some cell or to pin it, something down and hold it in place. And in this situation, I've done a fairly heavy polish, but then I've rotated the glass 180 degrees and polished it again. I do the rotation so the glass doesn't droop. If I do a heavy polish and I just polish it, say twice with this heavy polish, I don't rotate the glass, the tip will bend a little bit. And in this situation, I do want to bend the tip, and I'm going to bend the tip at the taper, at the shaft, and also at the shoulder of the taper. You might want to bend the tip because you're trying to get underneath an objective and you don't have a lot of room, or you want to have the tip come along the bottom surface of the plate where it's more like a hockey stick shaped pipette, and you want the taper from the tip a little bit back to be all in line and in focus on your microscope. So here's some examples of bending the tip. And here is a video on showing you how we're going to bend the tip at the taper, at the shoulder of the taper, and also at the shaft. Here, we've got a heat of ramp minus 100, and I'm holding it forward with my finger because I didn't have my fire polishing spacer to hold it in place. I bend it up, I turn off the heat, I slide the glass forward, and you can see I've got a nice bend there. And then I need to pull the glass through the filament the other direction so I don't damage the filament. You've got to be careful when you're doing this so you don't bend the filament or damage the filament. Here it is again. I had ramp minus 100, but in this situation I have ramp minus 50. And I'm bending it at the shoulder of the taper. And I'll pull the glass through it in the same manner, but I'm just showing you the bend there. And now I'm going to have the ramp test value because I'm melting the entire shaft of glass. If I try to push up too soon, it won't bend. So you've got to make sure you give it enough time to melt. Again, you want to be careful when you're doing this. You don't want to have too much beer or coffee in your system when you're doing this. Nice steady hands. The next section we're going to talk about cannulation pipettes. Pooneh Bagher I'm going to hand it over to Pooneh Bagher now, and she's going to talk about the application of her pipettes that we've been discussing today.
Before we switch to Pooneh, let me go back and introduce her real quick. Thank you very much, Adair, for this talk. It keeps amazing me what you can make of glass, and I called it glass art of a certain kind in one of my LinkedIn shares. I would like to encourage the audience to ask questions if there are any through the Q&A panel. I see there are a couple of questions already. We will have a combined Q&A session at the end of this webinar. Let me introduce our next speaker, Pooneh Bagher. She graduated at Cornell University, did a postdoc in Columbia, Missouri, went to Oxford, UK, was the course director in pharmacology there, and has recently moved to the TEM Health Science Center, and I understand is moving into her lab there and probably busy building things. And the title of her talk today is Experimental Applications for Micropipettes, Microvascular Physiologist's Perspective, and I'm looking forward to seeing how those pipettes that Adair showed us how to make them, how they can be used in real science.
Great. Yeah, so my name is Pooneh Bagher. I just want to talk to you a little bit about some experimental applications for the micropipettes that Adair nicely described to you. And so just a little bit of a background. I guess I've become a microvascular physiologist, and what this means is I study the function of blood vessels in diseased and non-diseased states, and I've used both in vivo and in vitro applications. So what I'm going to describe to you today are a couple of things. So pretty much micropipettes can be used for diverse applications, and I'm going to focus on 4 applications that I've used specifically in the lab. The first one, and I guess it's our bread and butter, is delivery of pharmacological agents using both pressure ejection or microiontophoresis. In addition, we can use these pipettes to disassociate cells, and so what we usually do is pair some of these pipettes with a controlled withdrawal and injection system so that we can really just gently disassociate the cells. We use pipettes pretty routinely for pinning tissues down, and in addition, what I probably use the pipettes for the most often is cannulating pipettes, and this can be for both in vivo as well as in vitro studies. And there's many more applications, and Adair kind of addressed many of them in her talk as well. So I just want to kind of note before I go any further that the examples that I'm going to describe today are pretty specific to the microvascular research field that I'm in, but really a lot of these techniques can be modified and they can suit numerous other experimental preparations in a lot of different fields. So I know some of the techniques that I'm going to describe here today people use pretty routinely in neuroscience and other fields as well. So even though I have a microvascular focus, it really is a very diverse technique that can be used in a wide range of fields. So first of all, we use pipettes for delivery of pharmacological agents. And really, the size of the pipette and the type of pipette you use depends on how you're going to deliver the pharmacological agent. So for instance, when you want to use pressure ejection, you usually use a pipette with a tip diameter of 3 to 5 microns, but you can also increase this depending on your application. On the other hand, microiontophoresis, which is how you deliver charged molecules, you typically have a tip diameter of less than 1 micron. And so I have an image here from a Journal of Visualized Experiments article that I published a number of years ago with my postdoc advisor, Steve Siegel. And in this, we showed how you can use microiontophoresis and micromanipulation in that particular application for intravital imaging, but once again, it can be applied to a number of preparations. And what you can see is this pipette has a pretty nice taper, and if we zoom in a little further, you can see that it actually tapers off to a very fine point, and you probably can't even see it in this image because it's so small. So really, we're working with an inner diameter of less than 1 micron for iontophoresis. Now what you do is you take these pipettes and you place them in a micromanipulator, and there are a number of micromanipulators out there, and really it just depends on what your purpose is. If you need to have fine control or coarse control or automated control, you can use a wide range of micromanipulators. But just to show you that you can then place these pipettes directly adjacent to the tissue that you would like to deliver the pharmacological agents. So in this particular preparation, this is an in vivo preparation where you're putting the pipette adjacent to a blood vessel. And so what you can do with this is deliver a pharmacological agents in a very focal, local, controlled manner. And this can be very useful not only for microvascular studies, but like I said, in other fields. In addition, we use the pipettes for disassociation of cells. The top image and the right image are from some of my colleagues, Matt Socha and Steve Siegel, where they were showing how to make an endothelial cell tube preparation. And the left image is some images I took as a postdoc with Chris Garland and Kim Dorr at University of Oxford. And basically what you do is you take your tissue and you place it in a variety of enzymes, and it digests away some of the outer layers. So what you do is gently pull the digested tissue in and out of the pipette, and that disassociates the cells. And it's these disassociated cells, which I can show you on the next image, that you then have in addition. You say, okay, well, I need to examine these and look at maybe calcium imaging or something else, but the tissue might have a difficult time staying still in your dish. So what we do is actually use the technique that Adair described earlier to fire polish a pipette until it's rounded at the end, and then we can use these fire polished pipettes to pin the tissue down into a chamber. So the top image here, you can actually see this is the tissue. This is an endothelial cell tube preparation. This is described further in the Jove article by Socha and Siegel. But you can see the pipette's kind of a ghost above it, and using micromanipulation, you place the pipettes directly onto the tissue. And the strength of this application is that you can then use micromanipulation to put a little bit of tension on these tissues to put them back at in vivo lengths. And the bottom image here is from the Jove article as well, where you can see they use the pinning pipettes. So really, these pinning pipettes can be very useful for situations where you have tissues that might otherwise kind of float away in your chamber. Probably one of the most useful applications, I essentially met Adair at a conference a number of years ago, and I was describing to her what I was doing. And she said, well, have you tried using these ceramic tiles to break your pipettes? And at the time, I had never heard of it. And really, talking to her changed the way that I make pipettes in the lab, and not only saved time, but also it made the pipettes more consistent. But what you can see in the top panel, these are cannulation pipettes. So what we do is isolate individual arteries or arterioles, and we cannulate them onto these glass micropipettes. And in the top image, we've actually broken the pipette using forceps and then fire polished it, in this instance with a microforge, but Adair described how you can use a Sutter pipette puller to do the same thing. And what I think you can clearly see is that with a forcep, you have a lot of variability in the edge. So on the right, you can see that this little bit is jutting out. On this other side, the pipette looks very different than it does on the right. Whereas on the bottom, these pipettes were broken or scored and broken with the Sutter Instrument ceramic tile, and then once again fire polished with a microforge. And what I hope you can see is that there's a really nice clean edge, and the two pipettes are very consistent in size. So using the ceramic tile, you can break a pipette and literally within 5 or 10 minutes make what otherwise would take hours to make. So really, when I learned this trick from Adair, it kind of changed my life, and my pipettes have been more consistent ever since. So I just want to acknowledge that I acknowledge the published materials where they were individually throughout the presentation, but some of the images are unpublished materials courtesy of Christopher Garland and Kim Dora at the University of Oxford, as well as myself. So thanks.
Thank you very much, Pooneh, for this instructive talk. I'm very pleased to hear how learning about this changed your life, and Adair is very willing to teach everybody her skills. It's really nice to see how it is used in scientific applications.
Great.
Let me introduce our last speaker in a sense. Telly Galiatsatos is going to host the Q&A session. I see there's a couple questions come in from the audience, and again, I would like to encourage you to use the Q&A panel, ask questions. We will either address them in the Q&A session or by email later today. Telly joined after graduating at the Queen's College in New York in 1987. He joined Instrutech when Instrutech was acquired by Hika Instruments in 2007. He joined Hika, and since last year, I have the pleasure and honor to call Telly my colleague again. He will host the Q&A session, and I don't think we need to change presenting, but we need to make sure you're unmuted. Telly, go ahead.
Thank you very much, Jan. Okay, we do have a few questions here, and we'll start off with Adair. So the first question is, what is the maximum length that can be achieved for a patch pipette with approximately 4 to 7 megohms?
Well, 4 to 7 megohms, I would predict, would be maybe a 1 to 2 micron tip, actually maybe a little bit larger if it was a short taper, but the longer your taper, you're also offering or adding in some resistance. So normally with a patch pipette, it's mainly the tip that's giving you that certain resistance reading. So basically, I would think that if you're pulling, you can pull those really long tapers and maintain a 1 to 2 micron tip, but with the taper that long, I'm really not sure what the resistance would be. So I guess you'd need to look at the result and see what the resistance is after you've filled it and put it in your bath. But you can pull a wide range of lengths of patch pipettes using the techniques that I showed you. So the answer is I don't quite know, but I think that with 4 to 6 megohms of resistance, maybe the taper length would be close to maybe 7 or 8 millimeters out.
Well, here's one for the P2000, so I'm not sure if it should be for you or should be for Jan. Who would like to take a crack at it?
We'll give it to Jan.
Okay, so the question is then, Jan, can long tapers also be made on a P2000 laser puller?
That's a very good question. The answer is that many of the principles that Adair showed today also carry over to the P2000 and potentially also to a couple vertical pullers. But one important principle is that higher velocity causes a longer taper. And we actually have a video on YouTube that shows the impact of the velocity on the taper length. So a lot of the pipettes that Adair showed today could also be made on a P2000 by increasing the velocity on the first line of a multi-line pull program. And then depending on whether you want to score and break the pipette, which if you use quartz works even better. That gives you perfectly square cuts and breaks. Or if you want to pull a tip that you could use, for example, for patch clamp in tissue, the trick is increasing the velocity in the first line of a pull program. So similar to a filament puller, the heat and the velocity setting have an impact on the length of the taper and also on the size of the opening.
Great, thank you. And here's another one for you, Adair. If I'm beveling to make a pipette to have a 30-degree bevel and a 25-micron opening, do I break the glass back first or just bevel the tip as it comes off the puller?
You'll want to break the glass back because your tip, when you pull the glass out really long, is under a micron, and you have to be beveling for a very long time to actually grind it all the way back to 25 microns. And you'd have to keep on repositioning the manipulator and driving the glass further down. That would take a lot of time, wear out the plate more rapidly, the beveling plate. So I would score it back using the glass-on-glass technique, and then take your tip that's broken a little bit, maybe under 25 microns, and then bevel it. And once it's beveled back a few microns back, it's going to be at about 25 microns when you're done.
Okay, thank you. Here's another one. When scoring a glass pipette with another glass pipette, do you use pipettes of the same size, shape, and taper? And then as a follow-up, how do you determine which part of the pipette to use for the scoring?
Okay, the second part of that, you're going to use the shoulder of the taper, the thicker part of the pipette, to score the other pipette at, maybe 25 or 50 microns, wherever you're scoring. Therefore, you're going to have a little bit of stiffer area of glass to push on the more flexible part of the glass, and that seems to work the best. It also works best when you score the glass right after you pull it. If you pull a lot of glass and put it to the side, all these long tapers, and come back and score it, it sometimes doesn't break as cleanly because once you pull the glass, it's still kind of curing, and I have found that during the time the glass is just kind of curing after you've pulled it, it's a little bit more receptive to being scored and broken. The first part of that question I didn't quite understand, Telly. Can you repeat that?
Yeah, sure. So when scoring a glass pipette with another glass pipette, do you use the same size, shape, and taper? So I guess between the two.
Size, shape, and taper. Well, I would, again, you pull two pipettes that are identical. You take you take the right one. That's going to be your scoring device, and you're going to score it in wherever you want to score it to break your pipette in your left hand. The one that you're using to score, that is just a scoring device. You don't want to go back and use that and score it and break it and use it as an aspiration pipette or a cannulation pipette because it's been scratched upon on these different locations along the larger part of the shoulder of the taper, and then it might break off when you try to use it. So your scoring pipette is just used for scoring. It's not used, you don't want to have that too as a final product.
So Adair, do you use the second pipette? So like the pair always to score?
Well, I'll have a separate pipette off to the side. I'll pull two pipettes. I'll use one of them to score. I'll keep that one off to the side. And then I can pull, actually what I've done since I'm pretty impatient, I tend to pull maybe 5 pipettes in a row, and then I hold up a bunch of pipettes, line up the shoulders of the tapers, and then I have my pipette where I've already scored one of them, and I know it's 100 microns, and I line it up with the ones that are unscored, and I score them all at the same time, and I make, maybe 500 micron pipettes at the same time, like a comb.
Sounds like serial production almost.
Yes, mass production.
All right, well, here's another one for you then, Jan. Is there a way to polish pipettes in the P2000?
That's a little tougher. The problem here is that the laser beam would need to be focused down onto a very small target, and that's not that easy to achieve. So it doesn't work the way Adair showed it for the filament pullers, and it definitely does not work for quartz.
Okay, great. Thank you. And here's another one for you, Adair. Is it necessary to fire polish cannulation pipettes?
I would say yes, because you are introducing it into a vessel or tissue, and you will damage the inner wall if you don't polish the tip a little bit. And also, you're usually tying the tissue to the pipette, and you're going to have some external force there pushing tissue against the edge of the needle, and you want to make sure that it's smooth and not going to damage the tissue as you're attaching the tissue to the needle.
I have accidentally used cannulation pipettes that weren't properly fire polished and have indeed damaged blood vessels when I was cannulating them. So I think in particular, if you're using it for the isolated blood vessel preparation, you'd want to fire polish them. And also disassociating cells, occasionally you can get digested tissue stuck to the pipette if it's not fire polished.
Thank you. Can the polishing and bending be done with a trowel filament instead of a box filament?
Yes, the trough filament requires a lower heat setting, so you need to be careful with the heat setting you're using. And then the polishing works just as well. The one thing that might even work better with the trough filament is when you're bending the tip upward, the trough is open at the top, so you can actually get a greater angle of degree of bend in the pipette. Normally you're limited to about 45 degrees with the box filament, and with the trough filament I've made some force probes. They clean 90-degree bend, so that's somewhat of an advantage if you're going to be bending the glass. You need a higher angle of bend at the taper or anywhere along the shaft or the shoulder of the tip.
Great. Well, actually, you mentioned something about the bending of the pipette, so this is a follow-up question based on that, which is, in the videos you showed the bending always going in the same direction, which was upwards. Is there a disadvantage or advantage in going in either direction?
Well, I always push it upward because I seem to have better control, and the block of the air jet is below, and I can use that as sort of a pivot point for the tool or the little number 5 Dumont that I tend to use to bend the glass upward. And I seem to be able to see it better that way. It's against the black background of the nylon that's behind the filament block assembly. The only disadvantage is if your heat's really high, your tip tends to droop back down after you've pushed it up. So that's why I encourage people to use a heat setting that's ramp minus 100 or ramp minus 50, something far under the ramp value. So when you bend the glass, it stays in that position before you turn off the heat. I guess some people might just turn on the heat, let the glass bend naturally and stop it without even pushing it with a device. That would be another approach, but where it stops bending, you probably don't have control and you might run into the filament. And you usually don't want to run into the filament with the glass. You're going to melt glass in the filament, or you might damage the filament, the shape of the filament, upon doing it in that manner.
Okay, thank you. All right, here's another one. What is the smallest and largest tip size that one can make by scoring and breaking using the glass-on-glass or the ceramic tile?
Okay. The smallest I can score and break using glass-on-glass with borosilicate glass is around 15 to 20 microns, but that proves to be somewhat difficult. If the taper's long at that point, it's super flexible. And as you guys saw, there's that one not so easy example video that shows me bending the glass, it's bending all the way over and folding in half practically, and it's not breaking. So that's more likely to happen when you try to break the glass under 25 microns. But I have found that if you use aluminosilicate glass, or maybe you might be using quartz glass, you might have a P2000 puller and you're pulling out quartz glass, that glass is about 10 times stronger, it's much stiffer, and I can do kind of more of a sweeping technique with the glass-on-glass approach, and I can make about a 7 to 10 micron clean break using aluminosilicate or quartz glass. The largest break I can make tends to be around 200, maybe 250 microns. You can break it larger, but you usually have to maybe rotate the glass as you're scoring it, so you get a more even score all the way around. The glass is so thick at that point that it doesn't always break cleanly, and also you tend to be closer to the shoulder of the taper when you're breaking it that large, and therefore it's also hard to kind of hit the right size when you're in an area that's more kind of cone-shaped. Finding the exact location where 350 might be is a bit of a challenge. I just made some tips for someone like that tip size. They're using them for cerebrospinal fluid collection, and they needed a tip that was around 350 microns. But it's a harder thing to do when you're scoring at the shoulder of the taper. So the largest I would say is about probably 200, 250 if you're using that one-sided manual pull where you have a really elongated taper.
Thank you. Here's another one for you. Can filamented glass be used for patch clamp?
It traditionally is used for patch clamp. I think some people, there might have been an old wives' tale out there where the filament, the glass, might plug the opening, or the filament might have a little sharp edge to it and might damage the membrane you're trying to patch onto. But that rod of glass that's called the filament, that's annealed to the inner wall of the glass, it starts off at 150 microns. And as you pull the glass out, it becomes smaller and smaller and smaller, and it's pretty much nanometer size when it gets to the tip. And it breaks off just very clean. You can't even detect it unless you're looking down the tip of the glass straight down the bore with an electron microscope. It's very hard to visualize. So the other thing you might run into if you're not using filamented glass is you have a harder time filling the glass. Most people backfill, and the filamented glass carries that solution to the tip more quickly, and also it carries the solution to the tip where you're less likely to have air bubbles. And so a lot of people filling their pipettes sit there and flick their pipettes, sometimes it goes flicking across the room. If you have filamented glass, you usually don't have to do much flicking, or you don't have to flick at all because there are no air bubbles in there to clear away.
You're off the hook now, Adair. This one is for Pooneh. Can you elaborate on cannulation experiments? Do you perfuse drugs or measure pressure?
So I don't measure pressure. In the particular experiments that I do, I actually keep pressure constant. Others do use a similar technique and measure pressure. So it really depends on your setup. But what we do is isolate blood vessels and put them onto the glass micropipettes, and we tie them off with sutures. And so the pipettes are fluid-filled lines, and usually you can change the height of the fluid-filled lines, so the columns behind the pipette, and therefore change the pressure in the lumen. So you can actually put the vessel at physiological pressures, or you can change the pressure to like high pressures or low pressures. There's a lot of variability in what you can do with that preparation.
Okay, well, here's another one for you.
Okay.
What is the difference of pinned versus not pinned tissue? Is it only for keeping it in place?
For the application that I use, we pin the tissue because the endothelial cell tubes can potentially float away in the bath. I mean, pinning tissues will just depend on your application, but for us, we use it to keep the tissue still. I think you can also actually use it to adjust tissue. So in other words, if you have a very delicate tissue in a chamber and you need to change the angle of the tissue so that you can, for instance, image something using a confocal microscope, sometimes you can use the micromanipulator and the pinning pipette to just adjust the tissue very delicately, so you don't have to use forceps or anything like that. So there's a lot of different applications with the pinning pipette. For what I showed you today, it's for holding the tissues down.
Okay, thank you. Well, here's one for you, Adair.
Right.
Can vertical pullers be used to make pipettes like you showed in your presentation?
Yes, they can. The vertical pullers are traditionally a one-sided pull. You might tend to get a longer taper, which is an advantage for some people. You might have a harder time finding longer, even regions of the taper in the 25 micron region. I've run into that before, but any area that's 25 microns or larger, you'll get a nice, long, even taper. Some pullers don't have a very even draw downward for making a really, really long taper. You might find some crookedness as the glass is drawn. we have a P30 pipette puller that has a 3mm trough filament in it, or you can get one that has a nicrofilament. And the newer version of the P30, we have a nicrofilament that has 4 winds. It's closer to the glass. You can actually melt aluminum silicate on that puller, and you can get some really long tapers, like 2 centimeter long tapers, which is pretty exciting. So the answer is yes, and in some ways, vertical puller, if you're really needing that long taper, can be an advantage.
Great, thank you. Now, there's a few other questions here, but I believe that they're going to be a little bit lengthy and will require more of an email approach and to actually be answered here live.
Okay. Let me thank the audience once more and also the presenters particularly for being here today. We will keep the webinar open for another 2-3 minutes so people can finish typing questions that they might be typing right now. Stay tuned for the notification about the YouTube and YouTube videos. And again, please fill in the survey that you're going to be guided to. And thank you very much again for being here. You have yourself a wonderful day or wonderful evening, depending on where in the world you are. Bye-bye.